Good evening and welcome to Physics 262 Pre-Lecture Notes. I'm Dr. Steve Brule. In today's lesson we'll study the magnetic field. We'll learn how to find the direction of a magnetic field by the direction a compass would point in such a magnetic field. We'll see how iron atoms are tiny permanent magnets that always have both north and south poles. We'll learn to find the magnitude and direction of a magnetic force that acts on a moving charge using the right-hand rule in the equation for magnetic force. And we'll memorize the conventions for communicating the directions of magnetic field and velocity in 3 dimensions. And we'll take the determinant of a 3x3 matrix to compute the cross product between velocity and magnetic field in IJK notation. Well, which way would a compass point if you put it near the end of the north end of a magnet? So here's a compass. We're going to put it near the north end of this magnet. Which way would it point? Well, let's go into a magic little program here and see what would happen. So here's a compass. There's take the compass away. So here's a magnet just sitting in space, and we don't even need to show the field. Let's now show the compass, and here's the compass, and we're going to hold it next to the north end, and it's pointing away. And the reason why it points away from the north end of this compass is because of the magnet is because the compass is itself a tiny little magnet. So it has a red end and a white end just like this magnet does. So since the north ends of magnets repel, similar poles repel and dissimilar poles attract. So we have the south pole of the magnet that is the compass being attracted to the north pole of this magnet, and the north pole of the compass is repelled from the north end of the magnet, so it ends up the red end, which is the north end of the compass, is pointing away from the magnet. And if I bring that compass over, well, I can map the direction of the field by just kind of moving this compass around, and I'd see which direction it has at any point in space. And as we go over to the south end of the magnet, we see that the compass points towards that south end. Well, let's return to our show. Well, wait a second. If we could, if we moved our compass all around in space and wrote down the direction of the magnetic field at every point in space, we'd have a map of the field lines around that magnet, around that permanent magnet. Okay, let's return to our show now. Okay, so that's what we just did. So magnetic field lines point away from north poles and towards south poles. And that gives rise to a popular misconception. Then a lot of students think that the north pole of a magnet is the same as a positive charge because the electric field points away from positive charge and towards negative charge, so that students think that, oh, well, south poles of magnets must be charged negatively and north poles of magnets must be charged positively. But that's not true. No, don't think that. Magnetism and electricity are related, but they're not directly related like that. We'll see how they're related later in the show. Well, this idea of using a compass to find the direction of a magnetic field works very well on Earth. And if we take the, let's go back to our little program here. Where is it? Here it is. So now instead of showing the magnet, we're going to show the Earth. And let's get rid of the field. So we can take our compass, and if you're on Earth, like here you are in Arizona, I just put us right there in Flagstaff, and we hold our compass, and it points in this direction, see? And if the compass, remember the north end of this compass is itself just a little magnet, so that north end must be attracted to the south end of the Earth, the south magnetic pole of the Earth. Well, how could that be? Let's return to our regularly scheduled program and see. The reason why that is because the, well, wait a second, I'm getting ahead. The North Pole of the Earth, which is not exactly, where is it? Wait. It's off to the right. So the North Pole, the geographic pole of the Earth is over here. We call that the North Geographic Pole. Geographic pole. And that's near the magnetic South Pole. There's a little confusion there when we first developed our magnets. We didn't know that magnets were, that the Earth was just a magnet and so forth. So we just said the direction of that the compass points is the direction that we're looking, and we'll call that direction north, and then we said, well, that must be the North Pole of the Earth. But really, we know now that north poles of our compass are attracted to south poles of magnets. So that's the south magnetic pole. Enough of that. So it turns out that the North Geographic Pole does not line up exactly with the Earth's magnetic pole. In fact, well, so this is called declination, so that when you hold your compass and it's pointing to the north, it's pointing to magnetic north, but true magnetic north for us in Flagstaff has a declination. I don't remember what it is. It's maybe 5 degrees or something. So our compass that we use to find north, those compi are a little off because of that. And what's interesting is every year that the South Pole and the North Pole are, well, I should have put them here because that's where the magnetic pole. The magnetic poles are shifting, and they go to Antarctica every year, and then they go and find where exactly the it would be the North Pole down here in Antarctica, and they find where it is, and they put a little stick in the ground. I wish I had a picture of that. I didn't think of that when I was making the video. But so they have these sticks that go back, I think, back into the 50s, and they're just, there they are. There's one, there's another one. That's good enough. Okay. Have you ever wondered why iron filings line up along magnetic field lines when they're near a magnet? Well, you'll know now. It turns out that every iron atom is itself a tiny little magnet with a north pole and a south pole. Every iron atom. And you can't split the atom to have just a north pole. You always have to have a north and south pole. We'll see why that is in a future show. In an ordinary piece of metal or iron, the magnetic fields of each atom are not lined up. See how they're all, the north poles and the south poles are just oriented in all different directions? But if we put this piece of iron near a magnet, then the atoms line up temporarily with the magnetic field that's being imposed on them. So here we're showing a piece of metal where all the atoms have been lined up, and then here's another piece of metal over here, and they're lining up with the magnetic field that's going this way. Here it's showing them perfectly lined up. In reality, they don't do that so perfectly. If you wanted to make a permanent magnet, what you do is you get a piece of iron, and then you put it in a magnetic field, so you get the atoms to line up, and then you heat it up. Heat it up so it gets really hot, red hot, but not, it doesn't melt, but it's almost. So then once it's really hot, the atoms are able to realign themselves, and then you allow that piece of metal to cool very slowly, and then you've locked in the orientation of all those little iron atoms, and you've created yourself a little permanent magnet. Okay, well, we're really getting into it now. Until 1820, everyone thought magnetism and electricity were completely separate fields of study. And this is a gentleman from the 1820s who thought that, obviously. Looking at a battery and holding a magnet, thinking that they didn't have anything to do with one another. But In 1820, Professor Christian Ørsted discovered that there was a relationship between electricity and magnetism. And the story is that he was giving a lecture in a class just like we might have here in Flagstaff at NAU. And he was doing a demonstration, and he had some compi on the table, and it was he was going from the chapter on electricity to the chapter on magnetism. So he had some demonstrations for magnetism and demonstrations for current. And then he noticed that when he turned the current on in his circuit and current started flowing through the wire, the magnets on the table turned around and oriented themselves in a certain direction that aligned themselves with the magnetic field that was created by the moving charges here. So then he discovered that magnetism and electricity were related, and he canceled class immediately to study this phenomenon. Well, a lot of people get Hans Christian Ørsted confused with Hans Christian Andersen, who was the famous Scottish physicist who put his finger in the dike to save Scotland from the flood. Well, next we'll consider what happens to a charge in a magnetic field. How does the force act on a charge that's in a magnetic field? Well, if the charge isn't moving, it's just sitting there and it's near a strong magnetic field, doesn't feel anything, no force if there's no motion. Isn't that interesting? So the charge has to be moving. This is an odd thing. And also, even if it's moving along a field line in the same direction or opposite direction of the field line, there's still no force that acts on this charge. But if the charge is moving across field lines, so there's a component of the velocity that is perpendicular to the magnetic field lines, the charge is strangely moved. And this is how it works. So let's say we have a magnet right here, and it's creating a magnetic field going this direction, and we've got this charge moving into the page. You're going to have to learn how to look at these diagrams that are portraying three-dimensional things in the two-dimensional plane of our paper. So if the magnetic field is going to the left here, and the velocity is going into the page, it will experience a force that's upward. Isn't that odd? You can also think of it as if velocity is in one direction and the magnetic field is in another direction, those two vectors always form a plane. They will define a plane, and the force will be perpendicular to the plane that is defined by the velocity and the magnetic field. We use the letter B for field, for magnetic field. So then you think, well, if the velocity's in this direction, the field's in this direction, I might have a force, and we know that the force is perpendicular to that plane that's defined by the field and the velocity. Well, the force could go in two directions, couldn't it? So how are you going to figure out which direction it goes? Well, Jimmy the Greek, this is, if you didn't follow sports back in the 70s, you probably didn't know that this guy's name was Jimmy the Greek. Great hair, Jimmy. So then Jimmy discovered a way to use his right hand. You put your thumb in the direction of V. Let's see, here's V. See, your thumb is in the direction of the velocity. Your fingies go in the direction of the magnetic field, and then coming out of your palm will be the direction of the force. This is we call this right hand rule number 1. And guess what? There's a right hand rule number 2 we'll learn later. Not in this show, but in a future show. And see how your thumb you can articulate your thumb to point in different directions for the velocity, and then your fingers will be in the direction of the magnetic field, and then out of your palm will come the direction of the force. Well, let's see how that works with a few examples. Well, first of all, we've got these two magnets. Here's a south pole and here's a north pole. What's the direction of the magnetic field in this region? Well, we know it points away from north poles and towards south poles, so there's your direction of the magnetic field that way. So if you put your thumb in the direction of the velocity, so put your thumb this way, and then your fingers are in the direction of the magnetic field, then your palm is pointing out of the page, isn't it? So the force on this particular charge would be pointing out of the page. So that's how we get the force when we know velocity in the magnetic field. If you have an electron, it's charged oppositely of a proton, so then you can use your left hand. They don't tell you that in the books, but it works. So left hand's for electrons, right hand's for positive charges. And if you're lucky, maybe we'll do this demonstration in class where we get a magnet near a electron beam and show how that electron beam is deflected. Okay, now to avoid confusion, memorize these following conventions for portraying direction on two-dimensional pieces of paper. First of all, we know that V is always going to be our velocity. B is our magnetic field. If you see on a piece of paper dots, that means that that's indicating a magnetic field pointing out of a page. And you can think of it like that's an arrow that's coming towards you, so you see the tip of the arrow. And then if you see little X's, you're looking at the rear end of an arrow that's going away from you. So that means that the magnetic field is into the page. Here, B is into page. And then this is going to cause confusion until you kind of get used to it. We're always trying to portray these three-dimensional motions on a two-dimensional sheet of paper, and it was easy when we were trying to portray two dimensions on a two-dimensional piece of paper because it's easy. It's just two dimensions on two dimensions. But now we have to think of out of the page into the page, and then if you have a piece of paper and you have a direction that's up, sometimes we'll call that north. Sometimes we'll call it up, or the positive y direction. But when you hear the word up, see, a lot of people have their piece of paper on their desk, and they think that up is towards their face. But no, up is towards the top of the page. And down is towards the bottom of the page, or the negative y directions. If we want to portray this direction, we might say east, we might say right, or the positive x direction. If we want to portray that direction on our page, we'll say west, left, or negative x direction. So we've got so many different ways to portray directions, and you might think, why don't we just settle on one? Well, because we don't. Okay, let's do a little example here. What would the direction of the magnetic force on this charge be if it was moving in a magnetic field that is portrayed by these dots? Press pause and think about that. Okay, what you should have come up with is you put your thumb in the direction of the magnetic field. So there's your thumb. And then your fingers in the direction of the... did I say magnetic field? That was velocity. So your thumb is in the direction of velocity. Then your fingers are going to be coming out of the page, pointing at us, right at our face as we're watching this. So then that means that the force is down. V cross B out, V to the right, B out of the page, and then your palm is pointing down, giving the force in this direction. Well, how about this one? Put your thumb in the direction of the velocity, fingers in the direction of the magnetic field, which is out again. So here's your thumb, and your fingers are pointing out of the page, so that gives a force in this direction. Oh, now we've got a negative charge, so I'm going to use my left hand, put my thumb in the direction of the velocity, and now my fingers are in the direction of the field, which is into the page. I don't know how to write that make a picture of that, but I'm getting an arrow that's going to the left. That's the direction of the force. What's the direction of the magnetic field on this charge? Well, now we're going to try to we have to find the field instead of the force. So then I'm going to put my thumb in the direction of the velocity. Thumb in the direction of the velocity there. And then my palm I'm going to point downward along with the force. And then I see that my fingies have to stick out of the page. I'm using my right hand. I hope you're playing along with this game. So that was out of the page. How about this one? This is a tricky one. What's the direction of the magnetic field on the charge shown? So V, put your thumb in the direction of the velocity. Put your fingers in the direction of the magnetic field. Oh, that is hard. I can barely stretch my thumb that much. But the thing here is we see that the velocity is either in the same direction of B, or if it's in the opposite direction of B, there's no force in that particular case. Remember that? And here's a nice one. V cross B, put your thumb in the direction of the velocity, fingies in the direction of the magnetic field, and the palm is now pointing out of the page. We'll have lots of time to practice that in class. How would you expect a force on a charged particle? What the magnitude of the force? Magnitude of the force if it's moving, if this particle is moving in a magnetic field. Well, I would expect that the stronger the magnetic field, the stronger the force would be. So we're looking at the magnitude of the magnetic force, and I think it's directly proportional to magnetic field. So if magnetic field goes up, force should go up. How about the charge on the particle? It's I would think that it was directly proportional to charge too, because if I want the magnetic force to go up if I have more charge. So that makes sense, doesn't it? Let me move this over so I end up having it look the way I want it to look in the end. How about the speed of the particle? Would the force be directly proportional or inversely? I think it would be directly proportional. So I think that the faster the speed of the particle, the stronger the force that charge would experience. And finally, the angle between the velocity and the particle. How will I throw something in there? Well, just off the top of my head, I think I would throw the sine of the angle in, because if the with sine, if the angle between V and B is 0, like in this case, then I would have sine of 0. That's not a 0. Sine of 0 equals 0. Or if V is in this direction and B is in this direction, then the angle would be 180, and I know that the sine of 180 is also 0. So by throwing this sign in there, I'm getting a factor that will give me 0 if the velocity and magnetic field are either in the same or opposite direction. And that is here we are. That is the formula for the magnetic force on a charge that is moving in a magnetic field. And another way to write that is, of course, this is V cross B. And we're going to learn how to do that right at the end of this show. Well, let's go back in time to the electric field. Remember, electric field was defined as force per charge. So that was in units of newtons per coulomb. Remember that? Electric field is electric force acting on a charge divided by the charge. And it didn't matter whether the charge was moving or stationary, did it? But with magnetic field, if we go back to our equation, we solve for magnetic field, so it's force over QV sine of theta. Then we see that the units of magnetic field are going to be newtons per coulomb, sort of like electric field, but then there also has to be this velocity unit back in there, because the bigger the velocity, the stronger the magnetic force is. On it, you figure it out. So the units of magnetic field is newtons. The units are newtons per coulomb, and then meters per second for that velocity. And if we had 1 newton, so then we can take the seconds and put it up here. So this is the unit for magnetic field, and we call this unit, if you have 1 Newton second per Coulomb meter, that's the unit of 1 Tesla, named after the famous American physicist Henry Finkelstein. Okay, well, let's say we have a charged particle. Oh, and this is an interesting particle because it's a proton and it's moving in the solar wind. Did you know that the sun actually is expelling protons into outer space as we speak? Little protons. And we call that the solar wind. So let's say that we have a proton moving at 500,000 meters per second, and it's coming in to the Earth. Let's see. Magnetic field of Earth. I keep wanting to make that the North Pole, but that would be the South Pole where the magnetic field is sticking away from it, isn't it? Nope, it is the North Pole. Okay, so the magnetic field points away from the North Pole. Oh, but it's the geographic South Pole. Oh, it's so confusing, isn't it? Well, anyway, so here's this particle coming in towards the Earth. It's encountering, it has a velocity in this direction. It's encountering the magnetic field of the Earth pointing in that direction. So it's coming in at an angle of 40 degrees to the Earth's magnetic field, which has a strength of 5 times 10 to the negative 5th Teslas, or I can write 50 microteslas. It's the Tesla, if you had a magnet that was 1 Tesla, that would be an incredibly strong magnet. Okay, so let's find the magnitude and direction of the force that acts on this proton. First thing we'll do is write our equation for magnetic force, put in the charge of a proton. There's the velocity of the proton. There's the strength of the magnetic field. And then we take the sine of 40 degrees. And there's the force then that acts on the proton moving near the Earth's magnetic field at an angle of 40 degrees. Well, then we can find the acceleration of that proton by just dividing the force by the mass of the proton, and there's the acceleration. We're going to do a lot more with motion of charged particles in magnetic fields in our next show. Okay, and finally, we also need to know how to work problems when we have the vectors velocity and magnetic field given in IJK vector notation. Well, in general, the way you take the cross product between two vectors, I just have 2 hypothetical vectors here, A and B. And for us, it's going to be V and B. Well, isn't that funny? B is also B there. Okay, so when we do this, the A vector is going to be velocity vector, so that's going to be Vx, Vy, and Vz for these guys. The way you do this, if you're computing a cross product, this is just it's very complicated on how to figure out what the cross product is when you have IJK notation. You don't just have the sine of the angle like we had before. So what you do is you take the x, y, and z components of the first vector and stick them in. First you say IJK at the top of your 3x3 matrix. Then you put the x, y, and z component of the first vector in for the second row, and then you put the x, y, you've probably seen this in your calculus class. You put the x, y, z components of your second vector in the third row of your matrix. Then you do something called taking the determinant of the matrix. And this has nothing to do with physics. It's just the way to remember how to figure out what the cross product is of these two vectors. And the way you do it, you cover up, first to find the I component, you cover up this little column below the I. It has nothing to do with the I. And you multiply AY times BZ. So it's going to be I times AY times BZ minus I times AZ times BY. See how that works? Then we'll take minus J, so we'll say there's our minus J times AX times BZ minus AZ times BX. It might seem complicated to you, but once you get used to it, it's not so bad. Then to find the K component, I'm going to, just like I got rid of this for the J component, I'm going to get rid of these two for the K. So I get rid of these two, and I think plus K times AX times BY minus AY times BX. It's nice, isn't it? That's all you have to do. So let's do an actual problem here. So let's say we have the velocity of an electron that's moving through a magnetic field with the magnetic field strength of 1 to -3 teslas given by that vector. All right. So the first thing we do is we write our IJK in our little 3x3 matrix, and then I put the 25, -10, and 15 in the slots for those in that second row, and I put the 1, 2, and -3 in the slots in my third row of my matrix, my little 3x3 matrix. Then I first compute the I component. I'm going to get rid of these two, and I'm going to have a -3 times -10 minus 2 times 15. -3 minus 2 times 15. There it is. I forgot one of my little parentheses there, it looks like. Okay, then to find the J component, I get rid of these and say it's 25 times -3 minus 1 times 15. There it is. And remember, that's minus the J. Students say, well, why should it be minus the J? And my answer to them is, why should it be anything? It's just the way it is. Okay, then to get the K, we get rid of these two. So it's plus K times 25 times 2 minus 1 times 10. And there it is. So then you compute all those little pluses and minuses, and you got that was -30, -30s. The negative signs really hang people up in here because it's a little tricky to kind of keep track of everything. So there we are. So now I have a little vector that is what V cross B is. But we don't want V cross B, do we? We want the force is Q times V cross B. So here's my V cross B right here. That's what this vector is. And then there's the Q in front of it. So then multiplying that Q through to each member of our little V cross B cross product, we get this vector as the force. And you'll see on the homework we've got quite a few problems practicing this. Well, what did we learn today? We learned to find the direction of a magnetic field by the direction of a compass that is moved around near whatever it is that we're trying to figure out the field. Iron materials are attracted to magnets because each iron atom is itself a tiny magnet. So that nail is made up of tiny little magnets that get aligned when they're close to an external magnetic field. We learned how to use the right-hand rule to find the direction of the magnetic force if we had the velocity in the magnetic field. And remember, we have to have that sign of the angle in there. It's a bit tricky to describe the 3 dimensions that we have to work with now on a 2-dimensional piece of paper. Up till now, we could do all our problems in 2 dimensions, but with magnetism, magnetism only exists if we live in 3 dimensions. If we lived in 2 dimensions, there wouldn't be magnetism. It's fun to take the determinant of a 3x3 matrix to compute the cross product between velocity and magnetic field. Thank you so much.